Ooh, I apologize about that last video ending abruptly. Somehow, I was never able to restart the program once I paused it. But anyway, we were about to investigate why multiplication and exponentiation of complex numbers is best done using polar representation. And to get us started, let's refresh ourselves, let's refresh our memories with regard to some standard trig identities. These are the sum and difference formulas for sine and cosine. And they are at the heart of multiplication and exponentiation of complex numbers in polar form. So we're going to refer back to these identities. And I don't know why I wrote them there, because I'm sure that we know these very well. Don't feel guilty. If we haven't used something in a while, we may need some reminders. So let's see. The sine of the sum of two angles, sine of the first, cosine of the second, plus cosine of the first, sine of the second. And with the addition formulas of sine, we have plus here, the sign stays the same. S-I-G-N sign stays the same. For the difference of two angles, sine of the difference of two angles, the sine S-I-G-N sign stays the same. Plus here, minus here. The sine of the difference of two angles, sine of the first, cosine of the second, minus cosine of the first, sine of the second. And the cosine of the sum of two angles, the sine S-I-G-N sign, changes. Plus to minus, minus to plus. Cosine of the sum of two angles, cosine of the first, cosine of the second, minus sine of the first, sine of the second. Cosine of the difference of two angles, cosine of the first, cosine of the second, plus sine of the first, sine of the second. Okay, let's multiply two complex numbers together. Here we have Z1 and Z2 in polar form, and we write their product here. And holy moly, how are we going to do this? Well, we can take the r's and multiply them together. And then just take what's in the parentheses and multiply them together. So we're going to get cosine of theta 1 times cosine of theta 2. And let's see. The i's, we can multiply those together. I times I is negative 1. And we'll have sine of theta 1 times sine of theta 2. So that's the real part right there. Everything else is going to be imaginary. Let's see. We have the first, we have the last. And then we have the outer first times last. So we have I times first times last. And okay. Tell you what, let me do the inner first. This one times this one. Sine theta 1 times cosine theta 2. So I just did the inners, this one times that one. Now let me do the outers. It's going to be cosine theta 1, sine of theta 2. Now let me see what we have here. Cosine, cosine minus sine, sine. So we're going to match that up with this thing. Cosine, cosine minus sine, sine. And son of a gun, this is the cosine of the sum of two angles. This thing, cosine of theta 1 plus theta 2. Now let's see, we got to match this horrible mess up with something. Sine of the first, cosine of the second, plus cosine of the first, sine of the second. That's this thing right here, the sine of the sum of the two angles. So this is sine of theta 1 plus theta 2, which gives us R1, R2 times the cosine of theta 1 plus theta 2 plus I sine theta 1 plus theta 2, period. Period. Now, the derivation of this result took a little bit of time, but this result is very powerful. Very, very powerful. Let's write down what we just found out. That's the formula. Essentially, we multiply the moduli together, and we take the cosine and the sine and just add the angles of each complex number. And we're going to extend this result in a few minutes. Now, before I look at division, let's extend this a little bit. But we've got n complex numbers that are denoted in this form. So z sub n would be r sub n times cosine of theta n plus I sine of n. And I'll write that out. Z sub n is r sub n cosine theta n plus I sine theta of n. So the pattern just continues. Well, here's what we get. We just take all of the moduli, r1 times r2 times dot, 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 r sub n, times the cosine, and we just add up all the angles. The cosine of theta 1 plus theta 2 plus dot, 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 theta sub n, plus I sine theta sub 1 plus theta sub 2 plus dot, 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 theta sub n, and we're done. So if we had to multiply a bunch of complex numbers together, we'd just do it this way. And it's a lot easier this way than it would be in rectangular form. Now, let me do another application of this multiplication scheme before we go to division. What happens if we square a complex number? Okay, we just take the product of the two moduli, r times r, so that's r squared, and then we just take the cosine and evaluate it at the sum of the angles. Well, the angles are the same, theta plus theta, so that's just 2 theta. And the same thing with the sine. So this is how we square a complex number. Well, what do you think would happen if we, instead of squaring z, we cubed z? Do we see a pattern here? This is what the pattern seems to be, and the pattern turns out to be correct. So we can extend this z to any whole number power is r to the n cosine of n theta plus I sine of n theta, and that holds for n equals 0, 1, 2, 3, 4, off into the sunset. So if I have a complex number and I want to raise it to the 20th power, I just take the modulus r, which is a whole number, raise it to the 20th power, and then take the angle theta, multiply it by 20 and stick it in here, I'm done. If I had to take the complex number z in rectangular form and raise it to the 20th power, I would literally have to multiply it by itself 20 times. And if we had a computer, an algebraic multiplication system, it would do that for us. If we had to do it with paper and pencil, I'm sure it would take well over an hour. And probably somewhere in that process, we'd make a mistake. The polar form for complex numbers is the way to go when we're multiplying or raising something to a whole number power. Absolutely. Now, let me just summarize this result because it's a biggie, and I don't just want to write it down. I want to write it down and encapsulate it in a box so that if we're taking notes, which I'm sure we are, this is going to be one that we highlight. That's a biggie. Whoops. It's only a biggie if we do it right. What's wrong here? Why didn't one of you raise your hand and tell me it? Don't go on and just let me make a mistake and not tell me. Tell me. Ah, yeah. Cosine n theta, sine n theta. Okay, I like that much better. The way to perform exponentiation in complex numbers, polar form. Now, division is oftentimes done best in polar form as well. Let's see what happens and why. Ha 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 ha. We look at this and we immediately don't like it because we're dividing by a complex number. And we're going to do here what we did when we were working in rectangular form. We're going to we're going to convert this into the quotient of a complex number and a real number. And we do that by multiplying by the conjugate. And the only thing that's troubling here is the cosine and I sine. The moduli, R1 and R2, that's not a problem. So I'm just going to multiply by the conjugate of what's in the parentheses. So I'll have cosine of theta 1 minus I sine theta 1 all over cosine of theta 1 minus I sine of theta 1. And what have we here? We're going to have R1 over R2. And we're multiplying wait a minute now. I take my vitamins every day, and I must have definitely taken my stupid pill along with the rest of my vitamins. What I don't like is having a complex number on the bottom. So I'm going to multiply top and bottom by the conjugate of the bottom. Okay. I'm not quite as dumb as I look. Close, but not as dumb as I look. Yeah, I want to get rid of the complex numbers on the bottom, so I'm going to multiply the bottom by its conjugate. And if I multiply the bottom by its conjugate, I have to multiply the top by the same number. Okay. Whew, that almost ended in catastrophe. Oh my goodness. Well, that shows what happens when we proceed without thinking things through carefully. Yep. And if I had thought things through carefully, I would have said to myself, this is the guy, this thing here on the bottom, which is a complex number, this is what I want to get rid of. I want to turn the bottom into a real number. And so I multiply the complex part, I multiply the bottom number by its conjugate, essentially, so that the denominator will be a real number. Now let's see. When we do that, we get the first thing squared plus, no, the first thing squared minus the second thing squared. So we take this thing and square it, but I squared is a negative number. And then when we square sine of theta, we get sine squared theta. Okay, now that's going to work out just dandy. And now the top, holy moly, I should have left myself more room. We're going to have cosine theta 1, cosine theta 2. I'm going to have to write small. And now let's see. I times negative I is just 1. So it's going to be plus, see, I times negative I is just plus 1. So I have 1 times sine of theta 1 times sine of theta 2. And now I'm going to get my imaginary term, I times something. Let's see. Before I wanted to do the inners, so I'm going to do the inners again. I sine theta 1, cosine theta 2. Okay. So sine of theta 1, cosine theta 2. And now I'm going to do my outers, cosine of theta 1 minus I sine theta 2. So cosine theta 1 minus sine theta 2 minus cosine theta 1 sine theta 2. And all of this goes right there. Now, let me just write that down again. Simplify it. R1 over R2 on the bottom, I have cosine squared theta 2 minus a negative sine squared theta 2. So let's see, what is this? This is just cosine squared theta 2 plus sine squared theta 2. Cosine squared plus sine squared of the same angle, that's just 1, isn't it? Holy moly. Cosine of the first, cosine of the second, plus sine of the first, sine of the second. Where do we see that? Cosine of the first, cosine of the second, plus sine of the first, sine of the second. That's the cosine of the difference of two angles. So this thing is the cosine of the difference of theta 1 and theta 2. Now let's look at this mess up here. Sine of the first cosine of the second minus cosine of the first sine of the second. Sine of the first cosine of the second minus cosine of the first sine of the second. Why, that's this thing here. Sine of the first cosine of the second minus cosine of the first sine of the second. And this is the sine of the difference of two angles. So this is the sine of the difference of theta 1 and theta 2. Son of a gun. Okay. This turns out to be very, very fundamental also. Let's enshrine this by putting this or encapsulating this also. Z1 over Z2 is equal to R1 over R2. Whoops. There we go. Cosine theta 1 minus theta 2 plus I sine theta 1 minus theta 2. Division is very, very easy in polar coordinates. Probably easier than in rectangular. So let's summarize all of this. Okay, any other typos up there that I should be ashamed of? No, I don't think so. let's see, the product of two complex numbers. The angles add, don't they? So cosine theta 1 plus theta 2 plus I sine theta 1 plus theta 2 and we can extend that result holy moly. Did that offend your mathematical conscience? I apologize. R1, R2, forgive me please. Z1 times Z2, R1, R2. The product of Z1, Z2 through Zn is the product of the moduli R1, R2, Rn. Cosine theta 1 plus theta 2 plus dot 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 theta sub n. And then the imaginary part, I sine theta 1 plus theta 2 theta sub n. And number 4, Z1 divided by Z2, that's going to be R1 over R2. Cosine of the difference So those are our multiplication and division formulas and exponentiation formula as well. So I think it's high time we did some examples. We've derived the formulas. Let's do some examples just to make sure we really understand what this is all about. Okay. You know what? I am going to make this exercise a little bit more forbidding to computation in rectangular form. Z to the fifth, if we're a glutton for punishment, we can do that in rectangular form. Let's do Z to the 10th. Even I'm not so much of a glutton for punishment that I do this in rectangular form. So let's see. Convert to polar. So R equals square root of x squared plus y squared. And that's 3 squared plus 3 squared, which equals 2 square root of, square root of 2 times 9, which equals 3 square root of 2. Okay. So R equals 3 square root of 2. Fine. Now, theta. Before I crank this out, I guess based on the discussion in the previous lecture, I need to know what quadrant that number's in. X is positive, Y is negative. Okay. It's what, fourth quadrant? So theta is equal to arctangent of y over x. Okay. So theta equals arctangent of y over x, which equals arctangent of 3 over 3. No, 3 over negative 3. So let's see, that's a negative 45-degree angle. So negative 45 degrees, that's negative pi over 4. Okay. Three square root of 2 to the 10th. And cosine of 10 times negative pi over 4 plus I sine 10 negative pi over 4. Holy moly, 3 to the 10th, I don't know. Square root of 2 to the 10th, I do know that. That's 2 to the 5th, or 32. You know what? I don't know what quadrant that's in. But see, 10 pi over 4, that magnitude is greater than negative 2 pi. So, you know what? If we add 2 pi to an angle, we get an equivalent angle, don't we? So, here's what I'm going to do. I'm going to add 2 pi to this angle. And let's see. You know what? I think maybe I want to add No, I like this. See, this is 8 pi over 4 minus 10 pi over 4 is negative 2 pi over 4, or negative pi over 2. Okay, I like that. Cosine negative pi over 2 plus I sine negative pi over 2. Oh, how about that? See, the cosine of negative pi over 2 cosine of negative pi over 2 is what? Isn't it 0? This turns out to be completely an imaginary number. Okay. And sine of negative pi over 2, that's negative 1, isn't it? Yikes. Now, if I had a calculator right about now, Ooh, that sure would be helpful. Let's see, do I have one? I need one, so I bet I don't have one. Oh, I don't have one. Oh my goodness. Well, let's see. 3 to the fourth is 81. So 3 to the fifth is 243. Okay. Okay, I think that's what it is. Son of a gun. Now, if we had had to do that with rectangular coordinates, that would have been a pain you know where. We don't want that. Okay, so this is a nice application. Let's do some more. We'll note for future reference that both of these are in quadrant 1. R equals square root of x squared plus y squared. So that's square root of 3 squared plus 1 squared. So R1 is 2. R2, square root of x squared plus y squared. And that'll give us 5 squared plus 5 squared. That's going to be square root of 25 times 2, which is 5 square root of 2. Theta 1 is the arctangent of y1 over x1. By the way, I should have been more careful there. Arctangent square root of 3 over 1. Now let's see. What kind of angles? Y1 there. That look better? What kind of angles are such that the ratio of sine to cosine is 1 over square root of 3? Wouldn't that be pi over 6, 5 pi over 6, 7 pi over 6, 11 pi over 6? And we're in the first quadrant, so pi over 6. Now, theta 2, arctangent of y2 over x2. So that's the arctangent of 5 over 5. Arctangent of 1. Yeah, so this is actually an easy one. X and Y are equal, and we're in the first quadrant. What angle in the first quadrant has X and Y coordinates that are equal? Or what angle in the first quadrant has sines and cosines that are equal? Pi over 4, right? Okay. So let's acknowledge our results. R1 is equal to 2. Theta 1 is equal to pi over 6. R2 is 5 square root of 2. And theta 2 is pi over 4. Okay. There. Now, Z1 times Z2, that's going to be R1, R2 times the cosine of the sum of the angles plus I times the sine of the sum of the angles. So that's going to be 2 times 5 square root of 2 cosine of theta 1 pi over 6 theta 2 pi over 4 I sine of theta 1, which is pi over 6, plus theta 2 pi over 4. And so that's 10 square root of 2 times the cosine of pi over 6 plus pi over 4. Let's see. 10 pi over 24, or 5 pi over 12. Okay. Plus I sine 5 pi over 12. And Z1 over Z2 equals R1 over R2 cosine of theta 1 minus theta 2 plus I sine theta 1 minus theta 2 and holy moly, what does that equal? R1 is 2, R2 is 5 square root of 2, let's see, pi over 6 minus pi over 4. So let's see, 4 is negative 2 pi over 24, or negative pi over 12. Now, if I multiply top and bottom here by square root of 2, I get a 2 on the bottom and 2. Well, let's see. Why don't I just divide top and bottom by square root of 2? So I'll get square root of 2 over 5 cosine of negative pi over 12 I sine negative pi over 12 and we will restate our results up here. Okay. This will conclude our lecture. I will send out some homework problems with these videos just to keep us busy. We want to be busy, don't we? But I will send out some homework exercises with these two lectures.